So now let's move on to one more non-ideality with the OTA. It is basically the thermal noise in the OTA, right? So yeah, let me actually draw the switch cap circuit once. Actually, before that, maybe I'll do at the end. Yeah. So as you know, with any resistor is going to generate thermal noise, and the way we model the noise in the resistor was to assume that our resistor is a good resistor, like all our parents. Their children is good, but their friends are bad, right? So the resistor is good, but the culprit is because you have hypothetical voltage source. The other way to model is to have a parallel current source. Okay, and the same is the case for an OTA. So a noisy OTA you can model either using voltage source in series with either of the two terminals, plus or minus. I'll just take plus for example, or at the current source. No, I will have it at the output because I have to add the current. See, current has to be added, right? So here is where the current comes along with the output current. I'm adding the noise current.
You used to have it over there, right?
No, you cannot have it here, right? Here, if you add, nothing changes, isn't it? If you have it at the input is open circuit, nothing will come. Okay, and this is Vn, and the path spectral density for the current, it is, you can think of it of the form 4 kt some gamma gm times I'll say n naught. You guys know what is k and t. This is, let us say, approximately 2/3 for a long channel MOSFET in saturation, and this guy you can think of it as an excess noise factor that simply takes into account the noise added by other blocks. See, basically to make an op-amp or OTA, along with this basic transconducting device, we need a whole bunch of transistors. They are not adding to the transconductance, but still they'll add noise, right? So this factor will take into account the noise of them. So if this is the current IN, this is the voltage Vn, what is the relation between Vn and IN?
Minus times of.
Forget about negative, right? It's okay. I mean Vn in terms of IN. IN by GM, right? So which means if I were to find Vn of f, it's 1 by GM square, so it will basically 4 kt gamma by GM times n0. So this is thermal noise. So let's quickly see what will happen or how we can analyze. I'll quickly draw the switch cap amplifier. 1, 2, 2. I'll also have a load, right? Great. So I'm considering noise, so I'll assume input is 0. So here all of these switches and the OTA will generate noise. We'll see how we can quickly find the voltage across CL, the output voltage at the end of I2. So we'll start by considering noise sources in one phase first. So first I'll consider noise sources only in the phase phi1, and in phi1 we have these circle switches active, so their on resistance will contribute to noise. So I'll draw the equivalent circuit now. So in phase 1 we have something like this for the input side. I'm combining the on resistance of both these into a single resistor for simplicity. Okay, so this is C1, C2, and similarly for C2 we'll have something like this. Right? Again, I'm combining the on resistance of these two switches into a single resistor. Now please recollect, if we have a switch, resistor and a capacitor, what was the mean squared noise of the samples?
KT by C.
It was only KT by C, right? And what was the path spectral density? No, 4 KTR is the for resistor, right? For the noise samples, what was the path spectral density? How?
White.
It was a white path spectral density.
With area.
So it's white PSD. Under what condition it was white?
But Fs is less
uncorrelated, so which means the time constant is much smaller than Ts by 2,
than Ts by 2.
and that's what we'll have with switches, so let's not worry about this. Okay, so now you should be able to say what is the mean squared noise voltage across C1, kT by C1. Across C2, what is the mean squared noise? kT by C2. In phase 1, this is what is happening. So let's see what happens in phase 2. In phase 2, we are simply transferring it. Okay. I will not consider the on resistance of the switches in phase 2 because we are ignoring their noises, right? So the on resistance will simply result in some exponential settling here and there, but we are only interested in the settled value. So I'll ignore the resistive effect. Okay. So what will happen now? Yeah, we'll consider the noise of these switches separately. Okay. So now what will happen? C1 already, okay, if this is voltage across C1, let's also write the charge, right? What is the charge? Mean squared value of the charge? Sorry?
C square.
kT C1. Okay, this time C1 square. Similarly, the charge in C2 is kT C2. Okay. So in the phase 1, capacitor C1 has sampled some charge. In phase 2, what will happen to the charge? It will get transferred to C2. Now C2 already had a charge of QC2. Now this QC1 will get added to it. So this is the total charge. So what is the mean squared value of this charge? It's sum of the mean squared values. That's because the two noises are uncorrelated. Okay. So this is the total noise charge or the mean squared value of the noise in C2. What is the output voltage? Remember, output voltage is same as the voltage across C2. So we know the charge stored in C2, mean squared value of it. So what is the mean squared value of the voltage across C2? No. From the we have the charge, right? From the charge, how will I find the voltage? By C2 square here, right? So you can work out this will be kT by C2. This is what will be. And this should logically make sense because we know that if you sample any input in the phase phi 1, that will appear at the output with a gain of C1 by C2. We are sampling a noise with this variance kT by C1 during the sampling phase, and that will appear with that gain square. Now during phase phi 1, we also sampled kT by C2 in C2, that will simply persist there. Okay. So this is just the noise in phi 1. Let's quickly do the noise in phi 2. Oops. So in phi 2, I'll remove these guys. So now we'll have all the switches here. I'll combine it into a single switch for now. Right? So we'll have basically noise from this switch, this switch, this switch, and also the OTA. Okay. So we'll have 4 noise sources. So if I were to find the mean squared noise at the output, first I have to find the power spectral density SV out of F, right? And how will I find the output power spectral density? I have 4 different noise sources. I'll take one at a time, say SVK of F. Find the transfer function from each noise source to the output. That is, let us say mod HK of F square. Do it for all noise sources. This will give the power spectral density. To find the mean square noise, I'll go and integrate this. You can do it. You can do it for the next 2 hours, but we'll try to simplify things because this is going to be really complicated, right? So we'll do a gross approximation. We already saw that the on resistor is going to be much smaller than 1 by GM, right? So I'll ignore that majorly noise is coming only due to GM, and the noise due to on resistance can be neglected. Okay, so that is going to simplify my things. I'll ignore all on resistance. This is a gross simplification, but just to get a feel for how calculations can be done, we'll do that. That's all. We'll only consider noise from the OTA. So this is IN, and now it's all simple because you already know that this circuit is a first order circuit. You know the effective resistance, effective capacitance at the output. So this simply boils down to this circuit. I have some R0, I have some C0, and what is the value of R0? 1 by beta GM. And what is the total capacitance at the output?
CN plus series combination of C1.
Okay, so it is this capacitor in series, in parallel with these two guys in series. Done. So this is the output side, and along with that we are also injecting a noise. That's all. Simple. So how will I find the, if this is V out, what is S V out of F? It is S IN of F times the transfer function from this current to the output voltage. And what is that?
I equals to V by.
Okay, let's write it then. So this is V out of F
Right.
in terms of the current IN of F. What is that? This is a Fourier transform, right? Fourier transform of the output voltage in terms of the current. What is that?
Just beta GM plus.
I mean, let's say write in terms of R0 and C0.
Acha.
What is it?
1 by R0. It's an equal 5. Okay.
I mean, it's parallel combination of R0 and C0, right? Parallel of R0 and C0. You should be able to remember these things now. It will be 1J 2 pi. It will be R by 1 plus SRC. These are some basic things. I hope you should remember these things. So this is the transfer function. So magnitude squared of the transfer function will come here, right? And that is going to be R0 squared by 1 plus 4 pi square F square R0 square C0 square, right? And I'll have to integrate it from 0 to infinity to get the mean squared value, right? So this is 0 to infinity, or let me hold on, 0 to infinity. Sin of F is 4 kt gamma gm times n0, that's a constant, times this R0 square I'll remove outside, it's a constant. So the only thing I'll have is square. So what is this integral?
1 by 4 R.
1 by 4 RC. Okay. I mean, this is a good result to remember, so please remember it. I mean, simple thing is, you guys know that if you have, just quickly say so that if you have an R and C, what is the mean squared value? KD by C. And remember, this is same as integral 0 to infinity. This is the noise voltage source. What is the part spectral density of this voltage source? So it's 4 kTr times the magnitude squared of the transfer function, which is 1 by 1 plus square BF. So it's basically 4 kTr times the integral. If this should be kt by c, what should be the value of the integral? Before us. So this is a good result to remember. We'll use it throughout the course. So this simplifies to 1 by 4 R0 C0. Right? I'll have to go to next page. So I have 4 kt gamma gm times n0. I had an R0 square, and the integral was 1 by 4 R0 C0. So 1 R0 goes, 4 goes. This is kt by C0 times gamma n0, gm R0. And R0 is, what is it? What is R0? 1 by beta gm. So gm goes. So basically have kt by beta C0 times gamma. So this is just the noise in phase phi 2. I mean, due to the noise sources in phase phi 2, we already computed the noise due to the noise sources in phi 1. Sum of these two will be the total noise. This is how we'll have to do. Great. So Great. So now I'll just mention one other trick or one other thing that you can use to find the mean squared noise of samples quickly. So let us say you have a circuit where you just have switches, resistors, and these resistors can be the on resistance of the switches, capacitors and inductors. We will not take inductors in our course. Let's say you have only a network comprising of these. It turns out if you want to find the mean squared value of output samples, again I will not go into details, I can point you to the relevant lectures. I think a couple of you might know. So what you have to do is you form what is called an adjoint network. The network is pretty simple. You don't do anything, you have the same network with R's and C's, switches. Here if the switches were controlled with the clock phi of t, you replace the clock with another clock phi hat of t, which is phi of minus t. Okay. And this is the output. So what you do is you inject an impulse current and you find the energy stored in the network at t equal to 0 plus. Energy will be stored only in capacitors, right? And you also find the energy stored in the network at t equal to infinity. Take the difference between the two, multiply by 2 kt. This will give Meansquared. Let's quickly look at some examples, you understand.
By any proof?
There is a proof, I will point you to lectures. It can be proved from basics of reciprocity and some extensions of time varying networks. Because the moment you have switch, it is not an LTI network, right? So it requires some understanding of time varying networks. I can point you to the lectures and resources. But anyways, this is the deal. Just take it for granted for now. We can look at examples to know how we can do it quickly. So let's say I will start with the simple guy. Right? So the phi is basically this. Okay. I am interested to find the noise samples sampled at the end of phi 1. I mean end of phi. I will define this as my t equal to 0. So I will form an adjoint network where things are same, just that this is phi of minus t. And phi of minus t is going to look like this. Right? And in this network, I will go ahead and inject an impulsive current. Okay. If I apply an impulsive current, sorry, that is R. If I apply an impulsive current, where will this current flow at t equal to 0? It will only flow through the capacitor. Irrespective of whether the switch is closed or not, the current impulse will only flow through the capacitor, right? So if it flows through the capacitor, what will happen to the voltage at t equal to 0 plus? It will change instantly, but what is the value? I mean, if I say delta of t current, I mean the area of the impulse is 1. What is that area of the impulse current is? Yeah. I mean, see, if I say I pump in a current of some 5 times delta of t, this is the area of the impulse, right? For a current, what is the area? Area of a current is what? Charge. So if I say that I am putting a delta of t current, it means I am putting 1 coulomb of charge into the capacitor. The charge in the capacitor is 1 coulomb. What is the voltage? 1 by C. So what is the energy stored in the capacitor? Half CV square, half C into, this is what? As t tends to infinity, what can we say about the voltage in the capacitor? Once the switch is closed, the resistor will suck out all the charges, it will be 0. So in the network, what is the energy stored at infinity? So the mean squared value is 2 kt times E0, which is 1 by 2C minus E infinity. That's simply kt with. It's a nice thing, right? Let's also look at another complicated example. I mean, complicated in the sense, if you do it, otherwise it is complicated. If you do it in this trick, it is simple. Let's say C1, C2. So now if you were to solve by brute force method, you will have to consider the noise per spectral density due to both of these guys, find out all the transfer functions and do it, right? But here you'll take the same approach. Let's say this is clock phi 1. This is clock phi 2. Let's say I'm interested to find the sample value at the end of phi 2. So I'll define this as my time instant equal to 0. I'll form an adjoint network. This is phi 1 hat. This is phi 1 of minus t. This is phi 2 hat. And I'll apply an impulsive current at the output. Now again, irrespective of whether the switch is closed or not, if I apply an impulsive current at t equal to 0 plus, where will the current flow? To the capacitor, right? Now remember that even if the switch is closed, we have a resistor here that will provide a very large impedance compared to the capacitor. Loosely speaking, capacitor acts like a short circuit for instantaneous changes, right? Yeah. For high frequency current, it acts like that. So at t equal to 0 plus, what is the voltage? Let's quickly do 1 by C2, right? So energy in this network is C2. At infinity, what happens? Basically, this capacitor is taking out charge from this and pushing it to ground. So what will be the final voltage? 0. So the mean squared value is basically 2 kt times. That's all. Okay. And just to remind you, this will only work as long as you have passive networks, passive elements like this, switches, resistors and capacitors. The moment you have, you can't use it. The moment you have OTA, this trick cannot be applied. That's something we have to remember. Only for passive networks you can apply it. So let's stop here.